a common source amplifier with an MOS transistor where the source is common to both the input and the output is a simple, straightforward one, and it's reasonable to always work with that to analyze first anyway. So if we take the output on the drain and the input is on the gate, let me mark those input. So the drain, gate, and source. The source is common to both the input and the output, so that's what we mean by common source. And we have a drain resistor, and we've got a small signal ground at VDD. So VDD is not actually ground, but from the standpoint of the small signals, it's ground. But right now, I don't want to do that. I wanted to show what happens for all large and small signals, what's going on for it basically. So we have V out is equal to VDD minus IDS RD. So ID is that current that's flowing between the source and drain. It's following this path. It doesn't go to the gate. And there's three possible equations. We have cutoff, saturation, and triode. For the drain current. So cutoff, and that occurs when Vn, which is equal to VGS in this case, is less than the threshold voltage. And in that case, we would have an output voltage. If we just write it that way, it'd be V out is equal to VDD minus ID RD, but that equals VDD minus 0, because in cutoff, the current is 0, which is equal to VDD. And then we have saturation, and that's for, we have to have it turned on, so VGS is greater than VT, but then we need to have VDS greater or equal to V overdrive, which is equal to VGS minus VT. So we have to kind of keep evaluating to make sure that we're always in that region. And in that case, then we'd have V out is equal to VDD minus 1/2 mu n Cox W over L times V overdrive squared times RD, right? That's the current. ID minus ID RD, and so we've got to make sure and put in that RD factor, and that's ignoring the channel length modulation factor lambda, or VA. And then we have triode, and that's for VDS is less than V overdrive, which is equal to VGS minus VT. And in that case, we have V out is still VDD minus that current times the resistance, but now the current, and there's a couple of ways we could write it, but we'll write it as mu n Cox W over L times V overdrive minus 1/2 VDS times VDS times RD. So three possible equations, and we could evaluate a situation. So let's say that we've got mu n Cox W over L is equal to 1,000 microamps per volt squared, or 1 milliamp per volt squared, and we've got VT is 1/2 volt. The threshold voltage, and we've got VDD is 2.5 volts, and a drain resistance of 12K ohms. So we've got everything defined in this amplifier now, basically, and we just want to see what those modes are of operation. So we could just pick some values of V in. Let's see, I'm not going to have enough room here. Let me try making a plot over here. We've got V out. V out is up here, and we've got V in is over here. And we've got 2.5 volts up here. So this would be 1.25, and this would be 0.75, something like that. Well, that's not quite right. 1.25, half of that is what 0.67 or something. We'll just leave it at that. So we've got V in, which is equal to VGS. And we can, if we know Vn, we can easily calculate V overdrive because that's VGS minus VT. And then we could find the current, IDS. And with that, we could find V out, which is equal to VDS. And then we should always check the mode. Which mode is it actually operating in? So for Vn is less than Vt, let's say 0.45 volts. That's less than Vt. That's pretty ugly, VGS. So if we had 0.45 volts on the input, so that would be somewhere down here. The overdrive, if it makes no sense, it would be minus 0.05, right? So that makes no sense whatsoever. IDS is 0 because it's in cutoff, right? And V out should be equal to VDD, which is 2.5 volts. In fact, it'll be that way all the way up to VT. We'll have this flat output all the way up to VT. And from that point on, we'll actually be in the saturation region. Right. So is that okay? Is that really true? So if we had an input of just above VT at 0.55 volts, then our V overdrive is 0.55 minus 0.5, or so it's 0.05. And we would have calculate a current of 1.25 microamps. And that would give us a V out of 2.49 volts, so just a little bit out, but we are in saturation because VDS is 2.49, and that's greater than V overdrive. So we just start to come down a little bit. We barely come down at all. There's hardly any change in the output. If we go up to 0.75, for Vn, VGS. Now we have VGS minus VT, 0.75 minus 0.5, so we have 0.25. And we'd get a 31 microamp current. And that would give us an output voltage of 2.125 volts. And 2.125 is definitely greater than 0.25, so we're still in saturation. And we're just starting to come down. So 2.1 would be down here somewhere, right? Something like that. And we could go up to 1.0 volts on the input. And V overdrive is now 1 minus 0.5 or 0.5. And we'd get a current of 125 microamps. And an output voltage of 1 volt. And 1 volt is larger than 0.5, so we're still in saturation. And we're just coming down. We're actually down to about here right now. I need a straight edge for that. At 1.05, we'd be at 0.55 and 151 microamps. and we'd have an output voltage of 0.69. So we're still in saturation because 0.69 is still larger than 0.55, and that's what we need for saturation. We need to have VDS is greater than V overdrive, so we're still in saturation. But we're getting close, right? So we're still in saturation, and our output voltage now, it's down, must be down around here somewhere. And something that would be useful to realize at this point is what is the maximum current? Well, the maximum current we would have would be VDD divided by RD, right? If all of the drop from VDD down to ground, if it all occurred in this resistor, then that would be the maximum current, right? The transistor doesn't drop any voltage. That would be the maximum. So that would be 2.5 over 12,000, and that equals 208 microamps. That's the maximum current we can get out of this amplifier. And at that point, V out must be 0, right? Does that make sense? So if we have no current flowing through here, or we have current, the maximum current flowing through here, but that means we have the entire voltage drop of VDD to 0 is occurring right here across that resistor. If that's all occurring there, then V out has got to be 0. So hopefully that makes sense to you. Think about some if that didn't. So we know that the maximum current would be out here somewhere, well, out here somewhere at 0, 0 volts on the output. But let's calculate up a little bit more. So 1.05, so 1.10. So we have a V overdrive of 0.60. And if we use the saturation equation, we get 180 microamps. And then we get a V out of 0.34 volts. Well, now this is less than that, right? VDS is less than V overdrive. So actually we've got to use the triode equation. And if we do, we'll actually get about the same result. We'll get about 0.34 volts. And it must be that we've come down very far, and we'll go into like that. So this region up here is saturation. We have cutoff up here, and triode over there. And that would give us limit. We need to stay in this linear region of saturation. It's not entirely linear, but it's the best region to produce a good linear, relatively low distortion output. So I'll always tell you that you need to find a Q point. And there's a couple of ways that you could find a Q point. You could just do halfway down. The Q point, if halfway down, you could do worse than choosing that. That's where the V out is equal to halfway down. Then we could find out, we could calculate the necessary current and the necessary input voltage for that. Or we could also say, instead of going all the way from VDD down to 0, we could say, well, let's pick between cutoff and triode, and that might be a more reasonable Q point, but that would be another one. So that would be for inputs of about 0.5 plus 1.1 over 2. That's equal to about 0.8 equals V in. at a different cue point. And then you might want to know what's the gain there. So it's the output over input, or the change in the output over the change in the input. And that would be the change in VDS over the change in VGS. And if we figure that out, we've got about minus 3.9 volts per volt would be the gain. That's actually not very high, but it's what we're getting out of this simple common source amplifier.